In 2011, a team in Australia found that the number controlling how strongly electrons grip their atoms appears to change depending on which direction you point a telescope. In 2005, two physicists at Imperial College found that the largest patterns in the leftover radiation from the Big Bang line up along a single axis that should not exist. And in 2021, a catalogue of 1.36 million quasars revealed that the sky itself is lopsided in a way that rejects the standard model of cosmology at 4.9 sigma. 3 different teams, 3 different decades, 3 completely different methods, and all 3 results point to the same patch of sky within about 10 degrees of each other. The probability of that happening by chance is less than 1 in a million. Tonight, we are going to walk through how a dying physicist's obsession with the number 137, a spectrograph calibration war between former collaborators in Australia and a cosmic axis that cosmologists named evil, all turned out to be chapters of the same story. And the reason that story was never assembled for you in one place is because the implication, if any of it holds, dismantles the single most important assumption in modern cosmology. Get comfortable, subscribe or join if you have not already. And if you want more of this across physics, deep time, and the mathematics underneath, the Patreon is where those wider explorations happen. Stay to the end of this one, because the instrument that will settle this question is being built right now in a desert in Chile, and the answer it delivers will either confirm everything we think we know or force us to start over. Let's ease into it. In 1933, Wolfgang Pauli checked into a clinic in Zurich. He was drinking too much, sleeping too little, and according to every account from that period, he was being slowly consumed by a single number. The number was 1 divided by 137. It is called the fine structure constant, and it controls the strength of every electromagnetic interaction in the universe. Every photon that has ever been emitted or absorbed, every chemical bond that has ever formed, every atom that has ever held together. This one number, approximately 0.00729735, determines whether any of it works, and nobody knows why it has the value it does. Nobody has ever been able to derive it from first principles. It just is what it is, and the entire structure of reality depends on it being exactly that. Pauli died in 1958, in room 137 of the Rotkreuz Hospital in Zurich. When he was told the room number, he reportedly said to his assistant, "I will never get out of here." He was right. He died there on December 15th, convinced that the number held a secret about the universe that physics had failed to decode. I am telling you this not as a quirky footnote. I am telling you this because 70 years after Pauli died in that room, a team of physicists in Australia published a result that did something to that number that should have been on the front page of every newspaper on the planet. They found evidence that the fine structure constant is not the same everywhere, that the number Pauli lost sleep over, the number that governs whether chemistry functions, whether stars can forge carbon, whether DNA can hold its shape, that number appears to change depending on which direction in the sky you look. And the direction where the change is most extreme, the axis along which the laws of physics appear to tilt, passes through us. That was 2011. It was published in Physical Review Letters. It had a statistical significance of 4.2 sigma, meaning the odds of the result being a fluke were roughly 1 in 30,000. And it should have detonated the foundations of modern cosmology, because the single most important assumption in all of cosmology, the assumption that the laws of physics are the same everywhere, is the assumption this result says is wrong. You have a name for this assumption. even if you have never heard it stated explicitly. It is called the cosmological principle. It says that on sufficiently large scales, the universe is homogeneous and isotropic. Same stuff everywhere, same rules everywhere, no preferred direction, no special location. Every equation in general relativity that describes the large-scale structure of the cosmos, every measurement of dark energy, every calculation of the age of the universe, every model of how galaxies formed and how they will die, all of it rests on this one assumption. It is the bedrock. It is the thing cosmologists do not question, because questioning it means questioning everything built on top of it. And the data says it might be wrong. Not from one measurement, not from one team, from multiple independent observations spanning different instruments, different techniques, different parts of the electromagnetic spectrum, all pointing in the same direction in the sky, within about 10 degrees of each other. That is the part that nobody seems willing to talk about. The fine structure constant is usually written as the Greek letter alpha. Its value, measured to extraordinary precision in laboratories on Earth, is 1/137.035999, 177, with an uncertainty of plus or minus 21 in the last two digits. That measurement comes from the 2022 CODATA evaluation, and it represents one of the most precisely known numbers in all of science. The relative uncertainty is 1.5 parts in 10 billion. To give you a sense of what that precision means, if you measured the distance from New York to Los Angeles with the same relative accuracy, you would know it to within the width of a single human red blood cell. The reason physicists are obsessed with this number goes beyond mere precision. Alpha is dimensionless. It has no units. It does not depend on your choice of measurement system. Meters, feet, furlongs. It does not matter. Alpha comes out the same regardless. And that means it is not just a human description of something. It is a property of the universe itself. Richard Feynman, who understood quantum electrodynamics better than perhaps anyone who has ever lived, wrote about alpha in his 1985 book QED, The Strange Theory of Light and Matter. He called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. He said, you might say the hand of God wrote that number, and we do not know how he pushed his pencil. Feynman was being precise about the mystery. It is not just that we do not know why alpha has the value it does. It is that we do not even know what kind of answer would count as an explanation. Is it derivable from some deeper theory? Is it random, a roll of the dice at the birth of the universe? Or is it, as some physicists quietly suspect, the result of selection effects? The fact that we can only exist in a universe where alpha falls within an extremely narrow range that permits complex chemistry. That last option is the one that connects to the Australian result in a way that should genuinely disturb you. Because if alpha is different in different parts of the universe, then the periodic table is different in different parts of the universe. The chemistry is different. The conditions for life are different. And the question stops being, why does alpha have this value? And starts being, why does alpha have this value here, where we happen to be standing? But I need to take you through this properly, because the story of how we got here involves a cast of characters you were never told about, an experimental technique that borders on the absurd in its ambition, a controversy that has been simmering for over 2 decades, and a convergence of evidence that is, as of right now, one of the most unsettling open problems in all of physics. It starts with quasars, and it starts with a man named John Webb. John K. Webb earned his Bachelor of Science at the University of Surrey in 1980 and his PhD from Cambridge in 1986. He spent most of his career at the University of New South Wales in Sydney, and he is now affiliated with the Institute of Astronomy at Cambridge and is a life member of Clare Hall. These are the kind of institutional credentials that usually insulate a physicist from the sort of scrutiny that comes with publishing uncomfortable results. They did not insulate Webb. What Webb set out to do in the late 1990s was conceptually straightforward, but technically almost impossible. He wanted to measure whether the fine structure constant had the same value billions of years ago as it does today. The way to do that is to look at the light from very distant quasars, the supermassive black holes at the centers of galaxies that are actively consuming matter and radiating enormous amounts of energy in the process. A quasar acts as a kind of cosmic backlight. Its light travels for billions of years through the universe, and along the way, it passes through clouds of gas. Those gas clouds contain atoms, metals like iron and magnesium and silicon and zinc, and those atoms absorb specific wavelengths of the quasar's light. The pattern of absorption lines is like a barcode, a chemical fingerprint of the gas cloud the light passed through. Here is where it gets critical. The exact wavelengths at which those atoms absorb light depend on the fine structure constant. Alpha appears in the equations that govern the energy levels of electrons in atoms. It enters through the relativistic corrections, the tiny adjustments that arise because the inner electrons of heavy atoms move at a significant fraction of the speed of light. If alpha were different at the time and place where the light was absorbed, the absorption lines would be shifted, not by much, by a few parts per million, but shifted in a way that is distinguishable from an ordinary redshift because different transitions in different atoms are affected differently. Some lines shift to the red, some shift to the blue, some barely move at all. The pattern of who shifts which way and by how much is a fingerprint that is unique to a change in alpha, and it cannot be mimicked by any other effect. The technique for extracting this signal is called the many multiplet method. It was developed by Victor Flambaum and his colleagues at UNSW, and it works by comparing multiple absorption lines from multiple different ions in the same gas cloud simultaneously. The older approach, the alkali doublet method, looked at pairs of lines from a single ion and was limited to maybe 1 part per 100,000 sensitivity. The many multiplet method improved that by roughly an order of magnitude, pushing into parts per million territory. It did this by exploiting the fact that different ions have different relativistic coefficients, called Q coefficients, which describe how sensitive each transition is to a change in alpha. Iron 2, for instance, has some transitions that shift strongly in one direction and others that shift strongly in the opposite direction. Magnesium 2 barely shifts at all, making it a useful anchor. By fitting all these transitions simultaneously against a model that allows alpha to be a free parameter, you can extract delta alpha over alpha, the fractional change in the fine structure constant, from a single absorption system. Webb's initial work used data from the Keck telescope on Mauna Kea in Hawaii. Keck is one of the largest optical telescopes in the world, with a 10-meter primary mirror, and its high-resolution Echelle spectrograph, called HiRes, was among the best instruments available for this kind of precision spectroscopy. Between 1998 and 2004, Webb and his collaborator, Michael Murphy, then at Swinburne University of Technology in Melbourne, published a series of papers analyzing quasar absorption spectra from Keck. They looked at roughly 140 absorption systems spanning redshifts from about 0.2 to about 4.2, meaning they were probing gas clouds that existed when the universe was between about 10 billion and roughly 2 billion years old. The Keck result was startling. The data suggested that alpha was smaller in the past, not by much, by about 5 to 7 parts per million. But the statistical significance was around 5 sigma, which in normal circumstances would be considered a strong detection. Murphy, Webb, and Flambaum published this in monthly notices of the Royal Astronomical Society in 2003 and 2004. The physics community did not react the way you might expect. There was no surge of follow-up experiments. There was no rush to confirm or deny. What there was, instead, was a kind of polite institutional silence. A few groups attempted their own measurements using different quasars and different instruments, and most of them found results consistent with zero variation. The explanation offered was straightforward and, on its face, reasonable. Wavelength calibration errors. The Keck spectrograph calibrates its wavelength scale using thorium-argon lamps, hollow cathode devices that emit light at known wavelengths. If those calibration wavelengths are slightly wrong, or if the spectrograph introduces distortions that vary across the detector, you could get a spurious signal that looks like a change in alpha. Webb did not accept this explanation, and what he did next is what turned a contested measurement into something far more dangerous to the standard model of cosmology. He went south. The Keck telescope sits in the northern hemisphere. It can see roughly 2/3 of the sky, biased toward the north celestial pole. Webb realized that to test whether the alpha variation was an instrumental artifact or a real cosmological signal, he needed data from a completely different telescope in a completely different hemisphere, looking at a completely different part of the sky. So he turned to the Very Large Telescope, the VLT, operated by the European Southern Observatory at Paranal in the Atacama Desert of Chile, latitude 24 degrees south. Its ultraviolet and visual Echelle spectrograph, called UVES, was comparable in capability to Keck hires, but was a different instrument built by different people with different systematic errors. The VLT data, which Webb analyzed with his PhD student Julian King and the rest of the UNSW team, covered 153 new absorption systems in the southern sky, and it showed something that nobody expected. Alpha was not smaller in the past in the southern sky. It was larger. Think about what that means for a moment. If the Keck data in the northern sky showed alpha was slightly smaller billions of years ago, and the VLT data in the southern sky showed alpha was slightly larger billions of years ago, then the variation is not just temporal. It is not just that alpha changes over time. It is spatial. Alpha is different in different directions. The universe has a preferred axis. When Webb and King combined the Keck and VLT datasets, 293 absorption systems spanning redshifts from 0.2 to 4.2. The result fit a simple mathematical model with disturbing clarity, a dipole. The same kind of pattern you see in the cosmic microwave background when you subtract out the monopole, a smooth gradient across the sky, higher in one direction, lower in the opposite direction. The amplitude of the dipole was approximately 0.97 times 10 to the minus 5, meaning the maximum variation from one pole to the other was about 10 parts per million. And the axis of the dipole pointed to a specific location on the sky. Right ascension, 17.3 hours. Declination, minus 61 degrees, with uncertainties of about half an hour and 9 degrees respectively. In galactic coordinates, that is roughly longitude 320 degrees, latitude minus 12 degrees, toward the constellations Ara and Triangulum Australe. The paper was published in Physical Review Letters, Volume 107, Article 191-101, in 2011. The statistical significance of the dipole model over a simple monopole was 4.2 sigma. The title was indications of a spatial variation of the fine structure constant. Indications, not proof, not discovery, indications. Webb was careful with his language, and that carefulness has been consistent throughout his career. As recently as 2024, on his profile at The Conversation, Webb wrote that we do not have definitive evidence of space-time variations, but 4.2 sigma is not nothing. In particle physics, you need 5 sigma to claim a discovery. In astrophysics, where systematic errors are harder to control, many landmark results have been published at lower significance. The accelerating expansion of the universe, the discovery that earned the 2011 Nobel Prize in Physics, was initially reported at roughly 3 to 4 sigma. The detection of the cosmic microwave background anisotropies by COBE was published at around 7 sigma. But those anisotropies were a factor of 10 larger than what Webb was looking for. At 4.2 sigma, the probability that the dipole is a statistical fluke is about 1 in 30,000, or 0.003%. The reaction from the scientific establishment was instructive. Sheldon Glashow, the 1979 Nobel laureate from Boston University, was quoted saying the importance of such a discovery would rank 10 on a scale of 1 to 10, and that it would rock physics and cosmology. In 2012, Webb, Murphy, and their colleagues won the Australian Museum Eureka Prize for scientific research, and the Sydney Morning Herald named Webb one of Sydney's most influential people. But outside of these recognition moments, the institutional response was characterized more by wariness than enthusiasm. And this is where the story starts to reveal something about how science actually works when a result threatens the foundation rather than merely extending it. I want to pause here and be precise about the nature of the criticism, because this is important. The people who challenged Webb's result were not cranks. They were serious spectroscopists doing serious work, and the criticism they raised was legitimate. The question was whether the Keck and VLT spectrographs introduced wavelength calibration errors large enough to fake the dipole signal. In 2015, Jeff Whitmore and Michael Murphy, the same Michael Murphy who had been part of Webb's original team, published a paper in Monthly Notices of the Royal Astronomical Society, Volume 447, page 446. What they did was elegant and devastating. They used a technique called supercalibration. They took spectra of stars that are nearly identical to the Sun, called solar twins, and compared the stellar absorption lines as measured by UVES and HIAS against the known solar spectrum measured by extremely well-calibrated instruments on the ground. Any difference between the two would reveal distortions in the spectrograph's wavelength scale. What they found was sobering. UVES showed long-range velocity slopes of up to 800 meters per second across 1,500 angstroms of wavelength coverage. HIAS showed slopes of up to 600 meters per second across 3,000 angstroms. These are not small numbers. The many multiplet method relies on comparing transitions separated by hundreds of angstroms across the detector. A slope of 800 meters per second across that range could mimic a shift of a few parts per million in alpha. The size and sign of the distortions were, in principle, large enough to produce a spurious dipole. This is the result that most physicists point to when they dismiss the alpha dipole. And, on its face, it is a strong objection. If your instrument introduces errors of the size needed to fake the signal, you cannot claim the signal is real. But there is a counterargument, and it deserves to be heard because it reveals something about the nature of this debate that gets lost in the summary versions. Valerio Dumont and John Webb published a response in 2017 in MNRS Volume 468, page 1568. What they did was incorporate the known spectrograph distortions directly into the absorption system modeling. Rather than treating the distortions as a reason to reject the data, they modeled them as additional nuisance parameters and asked what the data looked like after accounting for them. Their conclusion was that the dipole signal survived, though with inflated error bars. The significance dropped, but it did not disappear. This is where reasonable people can and do disagree. Whitmore and Murphy showed the distortions exist and are large enough to matter. Dumont and Webb showed the signal is robust to first-order corrections for those distortions. Neither group made an error. The disagreement is about how to interpret imperfect data when the systematic errors are comparable in size to the signal, which is one of the hardest problems in all of experimental science, and one that rarely gets the careful public discussion it deserves. What happened instead is what tends to happen in these situations. The physics community filed the result under interesting but probably systematic and moved on, not because the evidence demanded that conclusion, but because the alternative was too disruptive to engage with seriously. If the fine structure constant varies across the sky, then the cosmological principle is wrong. If the cosmological principle is wrong, then the Friedmann-Lemaitre-Robertson-Walker metric, the mathematical framework on which all of modern cosmology is built, is wrong. If FLRW is wrong, then our measurements of dark energy are wrong. Our estimate of the age of the universe is potentially wrong. Our models of structure formation need to be rebuilt from scratch. That is not the kind of implication that prompts a measured reevaluation. That is the kind of implication that prompts institutional immune response. And I want to be clear that I am not describing a conspiracy. Nobody sat in a room and decided to suppress Webb's result. What happened is what always happens. The result was uncomfortable. The systematic error explanation was plausible, and plausible was good enough for most people to stop thinking about it. Here is where the detail that should keep you up tonight enters the story. Because there have been follow-up observations, multiple groups, multiple instruments, multiple techniques, and the results are not unanimous, but they are far more interesting than the simple narrative of Webb was probably wrong would suggest. The most important follow-up observations targeted a single quasar called HE0515-4414, a bright southern hemisphere quasar at redshift 1.1508. This quasar has an unusually well-defined absorption system with multiple metal ion transitions clearly visible, making it one of the best single targets for a precision alpha measurement. In 2017, Sami Kotis, Michael Murphy, and Robert Carswell published a paper in MNRAS, volume 464, page 3679. They used UVES on the VLT with a signal-to-noise ratio of about 250 per pixel, which is extraordinary for quasar spectroscopy. Their result for this single system was delta alpha over alpha equals negative 1.42 plus or minus 0.55 parts per million, statistical plus or minus 0.65 parts per million, systematic, consistent with zero. No variation detected at this one line of sight. Then came the new instruments. In 2020, Dinko Milakovic and colleagues published work in MNRAS, volume 500, page 1, using the HARP spectrograph on ESO's 3.6-meter telescope at La Silla, calibrated with a laser frequency comb. A laser frequency comb is a fundamentally different calibration device that produces a spectrum of perfectly equally spaced, laser-sharp lines with frequencies known to 15 or more decimal places. It reduces wavelength calibration errors from the 100 meters per second level of thorium-argon lamps down to roughly 3 meters per second. Milakovic also introduced an AI-driven spectral modeling pipeline in a companion paper with Chung-Chi Lee and others in MNRAS Volume 504, page 1787, in 2021. The combination of laser calibration and machine learning removed two of the largest sources of systematic uncertainty in one stroke. And then, in 2022, came the result that was supposed to settle it. Murphy and collaborators used ESPRESSO, the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, on the VLT. ESPRESSO is specifically designed for the kind of extreme precision radial velocity work that alpha measurements require. It has a laser frequency comb calibrator. It feeds light from all 4 VLT unit telescopes simultaneously. It is, by a wide margin, the most precise spectrograph ever used for this kind of measurement. They pointed it at HE0515 minus 4414 for 16.1 hours of integration time. The result, published in Astronomy and Astrophysics, was delta alpha over alpha equals 1.3 plus or minus 1.3 statistical plus or minus 0.4 systematic parts per million, consistent with 0, the most precise single absorber measurement ever made, and it saw nothing. At first glance, this looks like the end of the story. The best instrument in the world looked at the best target available and found no variation. Case closed. But it is not closed. And the reason it is not closed is something that has been underappreciated in almost every summary of this debate that I have read. HE0515 minus 4414 is a single line of sight. It probes alpha at one specific position on the sky, and that position is not at the pole of the dipole. Think about what the dipole model actually predicts. It predicts that alpha varies as a cosine function of the angular separation from the dipole axis. At the poles, the variation is maximum. At 90 degrees from the axis, the variation is 0. HE0515 minus 4414 sits at an angle from the dipole axis where the predicted variation is small. The ESPRESSO null result is perfectly consistent with the dipole model. It rules out a monopole, a uniform change in alpha everywhere. It does not rule out a dipole. To test the dipole, you would need to observe multiple quasars scattered across the sky, including targets near the dipole poles, and measure alpha at each position with ESPRESSO level precision. That has not been done. As of right now, no experiment has been conducted that has the statistical power to confirm or refute the spatial dipole at the significance level needed for a definitive verdict. And then, in 2024, Webb himself, along with collaborators, published a paper titled The Mystery of Alpha and the Isotopes on the ArcSiv number 2, 401.00888. What they found was remarkable and deeply strange. They used ESPRESSO to look at two separate absorption systems in the same quasar, He0515-4414, at slightly different redshifts. The two systems gave inconsistent values of alpha at 7 sigma, an enormous discrepancy, but only if you assume that the magnesium isotope abundances in those distant gas clouds are the same as on Earth. If you allow the isotope ratios to be different, the 7 sigma tension disappears. This might sound like a technicality. It is not. The many multiplet method uses magnesium-2 as an anchor line because its Q coefficient is close to 0, meaning it barely responds to changes in alpha. But the wavelength of the magnesium-2 line also depends on the relative abundances of the 3 stable magnesium isotopes, magnesium-24, 25, and 26. If the ratio of these isotopes in a gas cloud 10 billion light-years away is different from what we measure on Earth, then the anchor line shifts, and the entire alpha measurement shifts with it. Nobody knows what the magnesium isotope ratio is in distant quasar absorbers. We assume it is terrestrial because we have no way to measure it directly at those distances. But that assumption could be wrong. It has been flagged as a potential systematic by skeptics for 2 decades. And Webb's 2024 paper showed that this one assumption, this single unverifiable input, can produce or erase a 7 sigma result. I want you to sit with that for a moment. The question of whether the laws of physics are the same everywhere in the universe may hinge on whether magnesium atoms 10 billion light-years from Earth have the same isotope ratios as magnesium atoms in a laboratory in Sydney. That is the state of this measurement. That is how close to the edge of our observational capabilities we are standing. But here is where it gets worse, because the alpha dipole is not the only thing pointing in that direction on the sky. In 2005, 2 physicists named Kate Land and João Magalhães, both at Imperial College London, published a paper in Physical Review Letters, Volume 95, Article 071301, with a title that most journals would have rejected on sight. They called it The Axis of Evil. What Land and Magalhães had found was an anomaly in the cosmic microwave background, the remnant radiation from the early universe that fills all of space at a temperature of about 2.725 Kelvin. The CMB is supposed to be almost perfectly uniform, the same temperature in every direction, with tiny fluctuations of about 1 part in 100,000 that represent the seeds of all future structure. Every galaxy, every star, everything. Those fluctuations can be decomposed into spherical harmonics, the mathematical equivalent of breaking a complex sound wave into its component frequencies. The lowest order harmonics, the quadrupole at L equals 2 and the octupole at L equals 3, describe the largest scale patterns in the temperature map. What Land and Magalhães showed was that the quadrupole and octupole were aligned with each other. Their axes pointed in nearly the same direction on the sky. This should not happen. In the standard cosmological model, the CMB fluctuations are random and isotropic. The orientation of the quadrupole should have nothing to do with the orientation of the octupole. They should be randomly oriented with respect to each other and with respect to everything else: the ecliptic plane, the galactic plane, the solar system. But they were not random. They pointed in roughly the same direction, toward galactic coordinates of approximately longitude 260 degrees and latitude 60 degrees, near the constellation Virgo, and the alignment extended to higher multipoles as well. Up to L equals 5, the data rejected isotropy at 99.9% confidence. The name Axis of Evil was deliberately provocative. It referenced the political phrase popular at the time, but the scientific meaning was clear. If the larger scale patterns in the CMB define a preferred axis, then the universe has a preferred direction, and the cosmological principle says it should not. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, detected the anomaly first. Cosmologists initially hoped it was an artifact of the instrument or of galactic foreground contamination. The fact that our own Milky Way radiates at microwave frequencies and that imperfect subtraction of this foreground could introduce spurious patterns. Then the European Space Agency launched Planck, a far more sensitive and better characterized satellite specifically designed to measure the CMB with unprecedented precision. Planck confirmed the alignment. The axis of evil was not an instrumental artifact. It was in the data. It was real. But it was not just the CMB. In 2009, Richard Watkins, Hume Feldman, and Michael Hudson published measurements of the bulk flow, the large-scale coherent motion of galaxy clusters. They found that clusters out to distances of about 400 megaparsecs were streaming at roughly 700 kilometers per second in the direction of galactic longitude about 282 degrees, latitude about 6 degrees. That is not far from the axis of evil direction. This bulk flow is much larger than the standard model predicts and points in roughly the same part of the sky. And then there was the hemispherical power asymmetry. When you split the CMB sky into two hemispheres along a specific axis, one hemisphere has more fluctuation power than the other. The asymmetry is statistically significant, and its axis is again roughly aligned with the axis of evil. This is three independent anomalies in the CMB data: the quadrupole-octopole alignment, the bulk flow, and the hemispherical asymmetry, all roughly consistent with a preferred direction in the universe, all detected by different instruments using different techniques. And now I need to tell you what happened when people checked whether the alpha dipole points in the same direction. In 2012, Antonio Mariano and Leandros Perivolaropoulos, physicists at the University of Ioannina in Greece, published a paper in Physical Review D, Volume 86, Article 083-517. The arXiv number is 1206.4055. What they did was compare the direction of the alpha dipole to the direction of another anomaly that had been found in Type Ia supernova data. Type Ia supernovae are the exploding white dwarf stars used as standard candles to measure the expansion rate of the universe. They are the objects whose study led to the discovery of the accelerating expansion and dark energy. When you map the apparent brightness of Type Ia supernovae across the sky, you find that the acceleration rate, and therefore the inferred dark energy density, varies with direction. There is a dipole. The universe appears to be accelerating slightly faster in one direction and slightly slower in the opposite direction. Mariano and Perivolaropoulos measured the angular separation between the alpha dipole axis and the dark energy dipole axis. They were separated by 11.3 degrees plus or minus 11.8 degrees. 11 degrees, two completely independent measurements, one from quasar absorption spectra measuring the fine structure constant, and the other from supernova brightnesses measuring dark energy. And their preferred axes on the sky were separated by about the same angle as your fist at arm's length. The probability of this alignment occurring by chance under the assumption that both directions are randomly distributed on the sky is less than 1 in a million. That is what Mariano and Perivolaropoulos calculated. Less than 10 to the minus 6. The two dipoles are not just vaguely in the same part of the sky. They are almost exactly aligned. Their 2013 follow-up paper, published in Physical Review D Volume 87, Article 043-511, arXiv 12.11.5915, added another axis to the comparison. They calculated the direction of the CMB maximum temperature asymmetry axis, which sits at galactic longitude 331.9 degrees, latitude minus 9.6 degrees. This axis was only 11.4 degrees from the alpha dipole. The dark flow direction was about 42 degrees away. Both papers noted that the alpha dipole axis lies in the same preferred plane defined by the CMB quadrupole and octupole alignment. I need you to understand what is being claimed here. It is not that one anomalous measurement might have a mundane explanation. It is that at least 4 independent probes of the large-scale universe, the fine structure constant measured from quasar absorption, the dark energy density measured from supernovae, the CMB temperature fluctuations measured by WMAP and Planck, and the bulk flow of galaxy clusters all show anomalies that point in roughly the same direction on the sky, within about 10 to 40 degrees of each other. And the probability that this is a coincidence is, by Mariano and Perivalaropoulos' calculation, astronomically small. Now, I need to add another piece to this, because the evidence has continued to accumulate since 2013, and the most recent additions are arguably the most striking. In 2021, Nathan Sechrist and colleagues published a paper in the Astrophysical Journal Letters, Volume 908, Article L51. They used the Catwise Catalog, a database of 1.36 million quasars identified by NASA's Wide Field Infrared Survey Explorer satellite. They measured the dipole in the number counts of these quasars across the sky. The standard cosmological model predicts a dipole in quasar counts because we are moving through space relative to the CMB rest frame. Our motion creates an aberration and a Doppler effect that makes quasars appear slightly brighter and more concentrated in the direction we are moving toward, and slightly dimmer and more spread out in the direction we are moving away from. This is called the kinematic dipole, and its amplitude and direction should match the CMB dipole. They did not match. The Catwise quasar dipole was about twice as large as expected from the kinematic effect alone, and it pointed in a direction that rejected the standard kinematic interpretation at 4.9 sigma. 4.9 sigma. That is just below the 5 sigma threshold for discovery in particle physics, and it came from 1.36 million objects, a sample size large enough that statistical flukes are essentially ruled out. In 2023, Lillian Dam, Geraint Lewis, and Brendan Brewer at the University of Sydney published a Bayesian reanalysis in Monthly Notices of the Royal Astronomical Society, Volume 525, pages 231 through 245. They confirmed the Catwise result at 5.7 sigma and found the dipole amplitude was 2.7 times larger than expected from the kinematic explanation. The direction was again roughly consistent with the same hemisphere of the sky where the alpha dipole, the dark energy dipole, and the axis of evil all cluster. I want to be careful here, because this is where the temptation to overinterpret becomes strongest. The directions of these various anomalies are not identical. They cluster in the same general region of the sky, within a cone of about 30 to 40 degrees, but they do not all point at precisely the same spot. And the angular uncertainties on some of these measurements, particularly the alpha dipole and the dark energy dipole, are large enough that the reported alignments may be partially inflated by posterior selection effects. The well-known problem that when you look for alignments after the fact, you tend to find more of them than are really there. This is a legitimate concern, and I want to flag it honestly. Mariano and Perivalaropoulos' p-value of less than 10 to the minus 6 assumes the two dipole directions are drawn independently from an isotropic distribution. If there is some residual systematic that correlates the two measurements, the true significance could be lower, and nobody has yet redone the alignment analysis with the newer Pantheon Plus or DESSN 5YR supernova compilations to check whether the dark energy dipole survives with updated data. But the counterpoint is also important. These anomalies were found by different groups, using different instruments, analyzing different types of objects with different physical origins. The alpha dipole comes from atomic absorption lines in gas clouds. The dark energy dipole comes from supernova brightnesses. The CMB anomalies come from microwave temperature fluctuations. The catwise dipole comes from infrared quasar counts. The bulk flow comes from galaxy cluster peculiar velocities. There is no known systematic error that could simultaneously produce correlated artifacts in all 5 of these independent probes. The instruments are different. The wavelengths are different. The analysis techniques are different. The foreground contamination sources are different. If all 5 are wrong, they are wrong for 5 different reasons that happen to produce results that all point in the same direction on the sky. That is not impossible, but it would be one hell of a coincidence. And this is the part that should make you angry. Because as of right now, you will not find a single mainstream science communication outlet, not a single documentary, not a single popular physics book published in the last 5 years that has put all 5 of these anomalies together in one place and said clearly what they collectively imply, that the cosmological principle, the single most important assumption in all of modern cosmology, has at least 5 independent empirical challenges, and those challenges are spatially correlated on the sky. That is not a footnote. That is not a curiosity. If it is real, it is the most important result in cosmology since the discovery of the accelerating expansion. And nobody is talking about it. I need to take you through what happens if the cosmological principle is actually wrong, because I think the full weight of this does not land unless you see what is built on top of it. The cosmological principle is not just a philosophical stance. It is a mathematical input. When Einstein wrote down the equations of general relativity in 1915, his field equations related the geometry of space-time to the distribution of matter and energy. The equations are extraordinarily complicated, a set of 10 coupled nonlinear partial differential equations. Solving them in full generality is virtually impossible. You need simplifying assumptions to make progress. In 1922, Alexander Friedmann, a Russian mathematician and physicist who would die of typhoid fever just 3 years later at the age of 37, applied the assumption of homogeneity and isotropy to Einstein's equations. What came out was stunning. The universe was not static. It was either expanding or contracting. The Friedmann equations, later refined by Georges Lemaitre, Howard Robertson, and Arthur Walker, gave rise to the FLRW metric, the mathematical description of space-time that underpins all of modern cosmology. Every measurement of the Hubble constant, every dark energy constraint, every calculation of the age of the universe at 13.8 billion years, every model of Big Bang nucleosynthesis that predicts the abundances of hydrogen and helium and lithium, every simulation of structure formation that shows how galaxies assemble from tiny density fluctuations, all of it depends on the FLRWD metric. And the FLRWD metric depends on the cosmological principle. If the universe is not isotropic, if the laws of physics or the distribution of matter have a preferred direction, then the FLRW metric is an approximation at best and wrong at worst. The expansion rate could differ in different directions. The inferred dark energy density could be a projection artifact, what you get when you fit an isotropic model to anisotropic data. The age of the universe could be different along different lines of sight. These are not hypothetical consequences. They are mathematical necessities. If the input assumption is wrong, the outputs are unreliable in ways that are difficult to predict without building entirely new mathematical frameworks. This is why the reaction to the anomalies has been muted. It is not that physicists do not understand the data. It is that they understand too well what the data implies if taken at face value. And the implications are so disruptive that the psychological cost of engaging with them seriously outweighs the reputational benefit of being early to a paradigm shift that might not happen. This pattern has repeated itself throughout the history of physics, not as conspiracy, as institutional self-preservation. The same immune response that kept Boltzmann's statistical mechanics at arm's length until after his suicide in 1906. The same reflex that dismissed Alfred Wegener's continental drift as delusion until plate tectonics arrived in the 1960s, 3 decades after his death. The same instinct that led Werner Heisenberg to declare in 1927 that the game was now won, meaning that the Copenhagen interpretation had settled the measurement problem, when in fact it had merely declared the question unanswerable. The mechanism is always the same. A result threatens the framework. The framework is too useful to abandon. The result is filed under interesting but probably wrong. And decades pass. Let me tell you what the theorists say, because there are theoretical frameworks that could explain a varying alpha, and some of them are far more developed than you might expect. The simplest is the Bekenstein-Sandvik-Barrow-Maget-Hojo model, usually abbreviated BSBM. Jacob Bekenstein, the same physicist who calculated the entropy of black holes and helped lay the groundwork for the holographic principle, proposed in 1982 that the electric charge E, and therefore alpha, could be promoted from a constant to a dynamical field. In this framework, E is not fixed by the laws of physics. It is a scalar field that evolves over time and varies in space, driven by the density of charged matter. John Barrow and João Magalhães, yes, the same Magalhães who named the axis of evil, developed this into a fully relativistic cosmological model in the late 1990s and early 2000s. The BSBM model makes specific predictions from the original Webb-Keck data suggesting delta alpha over alpha of about 5 parts per million over a look-back time of 10 billion years. The model infers a present-day rate of change of alpha of roughly 1.1 times 10 to the minus 16 per year. That rate is far below the current experimental limits from atomic clock comparisons, which constrain the rate to less than about 2 times 10 to the minus 15 per year, based on measurements comparing ytterbium ion clocks to cesium atomic clocks, published by Eckhard Paik and colleagues in 2004. So the BSBM model is consistent with the atomic clock null results. It predicts a variation that was larger in the past and has been exponentially damped by the onset of dark energy domination, which began about 5 billion years ago. The field that drives alpha variation essentially freezes out as the universe transitions to accelerating expansion. But BSBM explains a temporal variation in alpha, not a spatial dipole. For the dipole, you need something else. One possibility is a domain wall. In particle physics, a domain wall is a topological defect, a boundary between regions of space where a scalar field takes different values. Think of it like the boundary between 2 magnetic domains in a bar magnet, where on one side the magnetic moments point up, and on the other side they point down. If the scalar field that determines alpha has multiple possible ground states, which is exactly what the string theory landscape predicts, then the universe could contain domain walls, where alpha transitions from one value to another. If our observable universe happens to straddle such a wall, or if we sit near one, then alpha would appear to vary with direction, exactly as the dipole suggests. Mariano and Perivolaropoulos explored a specific version of this in their papers. They considered a model where the observer sits off-center inside a horizon scale. Topological defect, a monopole in the scalar field that controls alpha. In this geometry, you naturally get dipoles in both alpha and the cosmological constant that point in the same direction, because both are driven by the same underlying field. The alignment of the alpha dipole and the dark energy dipole, the alignment that has a probability of less than 1 in a million of occurring by chance, emerges automatically in this model as a geometric consequence. This is worth sitting with. There exists a theoretical framework grounded in scalar field theory and consistent with the string theory landscape that predicts exactly the pattern of anomalies that the data shows. An alpha dipole, a dark energy dipole, and an alignment between the two. The model was not constructed after the fact to fit the data. The topological defect monopole geometry was studied independently, and the prediction of correlated dipoles is a natural consequence of the math. But there is a constraint that makes this harder than it sounds. The equivalence principle, the foundational postulate of general relativity that says all objects fall at the same rate, regardless of composition, places severe limits on any scalar field that couples to electromagnetic physics. If a field controls alpha, and alpha affects the masses of atoms, then the field effectively gives different atoms different gravitational masses, violating the equivalence principle. The Eötvös experiments, which compared the free fall rates of different materials to extraordinary precision, and the European Space Agency's microscope satellite, which tested the equivalence principle in orbit in 2017, both found no violation down to parts in 10 to the minus 15. Thibaut Damour, at the Institut des Hautes Études Scientifiques near Paris, argued in 2003 that these constraints essentially require any alpha-varying scalar field to be nearly frozen today, making a 10 to the minus 5 variation over a Hubble distance difficult to accommodate without extreme fine-tuning. This is the bind. The data hints at a spatial variation. The theory can accommodate it, but the constraints from other experiments make it hard to build a model that explains the alpha dipole without violating something else. It is not impossible, but it requires assumptions about the coupling constants of the scalar field, about the energy scale of the domain wall, about the distance between the wall and our location that are currently unconstrained by data. And this is where I need to tell you about a development from October 2025 that almost nobody has heard about, because it happened in a nuclear physics laboratory in Vienna and has implications that reach far beyond its original context. A team led by Thorsten Schumm at the Technische Universität Wien published a paper in Nature Communications, Volume 16, Article 9-147. What they had done was use the thorium-229 nuclear isomer transition, a phenomenon that had been sought for decades and was only recently brought under laser control, to measure the sensitivity of a nuclear clock transition to changes in the fine structure constant. The thorium-229 isomer has an energy gap of only about 8.4 electron volts, extraordinarily low for a nuclear transition. This makes it exquisitely sensitive to changes in fundamental constants, because the energy gap depends on a near-exact cancellation between the electromagnetic and strong nuclear contributions. Any change in alpha shifts the balance of that cancellation far more than it would shift an ordinary atomic transition. The enhancement factor they measured was K equals 5,900, plus or minus 2,300. What this means is that a thorium nuclear clock would be roughly 6,000 times more sensitive to changes in alpha than the best existing atomic clocks. If alpha is drifting at the rate the Webb data suggests, a thorium nuclear clock would detect it. Not eventually, not in principle, within a few years of continuous operation. This is a laboratory test of a cosmological hypothesis, and it is being built right now. The first thorium nuclear clocks are under construction at multiple laboratories around the world. If alpha is changing at even a fraction of the rate implied by the quasar data, these clocks will see it. But even the nuclear clock tests face the same limitation as the ESPRESSO measurements. They test for temporal variation at our location. The dipole is a spatial variation. To test the spatial dipole directly, you need to measure alpha at multiple positions across the sky with instruments that have definitively eliminated wavelength calibration systematics. There is one instrument that can do this, and it does not exist yet. The Extremely Large Telescope, or ELT, is being built right now by the European Southern Observatory on Cerro Armazones in the Atacama Desert of Chile at an altitude of 3,046 meters. Its primary mirror will be 39 meters in diameter, making it by far the largest optical telescope ever constructed. The mirror is composed of 798 hexagonal segments, each about 1.4 meters across, and the total collecting area is roughly 10 times that of the VLT. First light is targeted for late 2031 or early 2032. Among its suite of instruments is one called ANDES, the Amazones High Dispersion Echelle Spectrograph. ANDES is specifically designed, among other science goals, to measure variations in fundamental constants and to detect the real-time expansion of the universe through the Sand-Age Lobe redshift drift effect. Its forecast photon limited precision for measurements of delta alpha over alpha is 0.3 parts per million. That is 3 times more precise than the best ESPRESSO measurement on a per-system basis. And with the 39-meter collecting area, it will be able to observe far fainter quasars in far less time, opening access to absorption systems scattered across the entire sky, including targets near the poles of the alpha dipole. ANDES, with laser frequency cone calibration on the ELT, is the experiment that will either confirm the dipole or kill it. If the dipole is real at the roughly 10 parts per million level claimed by Webb, ANDES will see it clearly in a sample of a few dozen carefully selected absorption systems distributed across the sky. If the dipole is an artifact of Keck and VLT calibration errors, ANDES will see zero variation everywhere with enough statistical power to close the case. The waiting period between now and 2031 is itself part of the story. It means we are living in a window of genuine scientific uncertainty, where one of the most fundamental assumptions in all of physics, that the laws of nature are the same everywhere, is empirically contested and has not been definitively resolved. This is not the way science is usually presented. Usually you hear about the discovery after the verdict is in. You are told what was found, what it means, and why it matters, all in the past tense. This is different. This is happening right now. The question is open, and the answer, when it comes, will either confirm everything we think we know about cosmology or force us to rebuild it from the foundations. But I want to go deeper than the experimental timeline, because there is an implication of a varying fine structure constant that does not get discussed in the literature, and that I think is the most unsettling part of this entire story. If alpha varies across the sky, then chemistry varies across the sky. Not metaphorically, literally. Alpha enters the equations that determine the energy levels of electrons in atoms. It controls the strength of every electromagnetic interaction. It determines the wavelengths at which atoms absorb and emit light, the strength of chemical bonds, the rates of every chemical reaction. If alpha changes by even a few parts per million, the energy levels of every electron in every atom shift. The wavelengths of every spectral line shift. The rates of certain chemical reactions change. At 5 to 10 parts per million, the effects are tiny. No chemical bond is going to break. No atom is going to fall apart. The periodic table at 10 parts per million deviation looks almost identical to ours. Your chemistry textbook would still work. But that is at the current claimed level of the dipole. The dipole amplitude is measured at those quasar redshifts, which probe distances of billions of light years. The question is what the variation looks like at even larger scales, beyond the observable universe, or in the deep past, or in regions where the scalar field that drives alpha has settled into a different vacuum state entirely. The string theory landscape predicts something on the order of 10 to the 500 different possible vacuum states, each with different values of the fundamental constants. This is an absurdly large number. If you wrote down one vacuum state per atom in the observable universe, you would need more universes than there are atoms to catalog them all. Each vacuum state corresponds to a different configuration of the extra dimensions that string theory requires, and each configuration gives different values of the coupling constants, including alpha. In most of these vacua, alpha is nothing like 1 over 137. In most of them, atoms as we know them cannot form. Chemistry as we know it does not function. Life as we know it is not possible. The standard response to this embarrassment of riches is the anthropic principle. We observe alpha to be 1 over 137 because only in a region where alpha takes that value can observers like us exist. The other vacua are out there, realized in other bubbles or other branches of the eternal inflation landscape. But nobody is there to measure alpha because nobody can exist there. This is a logically consistent position. Many physicists hate it because it is not predictive, because it substitutes explanation for selection, because it feels more like giving up than like discovering something. But if you take the landscape seriously, then the question, why does alpha have this value, has a straightforward answer. It has this value here because we are here, and we can only be here if it has approximately this value. Now watch what happens when you add the alpha dipole to this framework. If alpha varies across the sky, it means we are not just in a universe where alpha works for life. We are in a specific location within that universe where alpha works for life. And the variation implies there are nearby directions, cosmologically speaking, where alpha is shifting toward values that might be less hospitable. The full anthropic picture would then look like this. The eternal inflation landscape produces bubbles with different vacuum states. Within each bubble, the scalar fields that determine the fundamental constants can have spatial gradients, topological defects, domain walls. Life arises at positions within bubbles where the local values of the constants fall within the habitable range. We are not just in the right universe, we are in the right part of the right universe. And the dipole is the first observational hint of the gradient, the first signal that the values are not uniform, that we are sitting in a habitable patch surrounded by regions where the numbers are drifting. Fred Adams, a physicist at the University of Michigan, published a comprehensive review in Physics Reports in 2019, volume 807, page 1, examining the fine-tuning of the fundamental constants for life. His analysis was more nuanced than the popular "if you changed alpha by 1%, life would be impossible" story that gets repeated in popular science. He found that the habitable window in the parameter space of alpha the gravitational coupling constant, and the strong force coupling is considerably wider than fine-tuning advocates typically claim. Life is not balanced on a razor's edge. There is a range of alpha values, perhaps plus or minus a few percent from our value, where complex chemistry could function and stars could produce carbon. But here is the crucial point. A few percent is enormous compared to the 5 to 10 parts per million variation claimed by the dipole. The current data, even if confirmed, does not put us anywhere near the edge of the habitable window. What it does is establish the principle that alpha can vary, that the constants are not locked in by some fundamental symmetry, that the numbers are not the same everywhere, and if they can vary by 10 parts per million across 10 billion light years, the question becomes how much they vary across distances we cannot observe, across the full extent of the bubble we inhabit, across the boundaries between our bubble and the next. And this connects to something that I think is the real reason this result disturbs physicists at a level deeper than methodology or systematics. It is the question of whether we are at the center. A dipole has two poles. By construction, the axis of the dipole passes through the observer. If you measure a dipole in any quantity from Earth, the axis of that dipole will always pass through Earth. That is just geometry, not evidence of a special location. The same would be true for an observer at any other position in the universe. They would also sit on their own dipole axis. But the coincidence is not that the alpha dipole passes through us. All dipoles do. The coincidence is that the alpha dipole, the dark energy dipole, the CMB anomalies, and the quasar count dipole all have axes that cluster in the same region of the sky. If you were at a different position in the universe, these different dipoles would generally point in different directions. The fact that they align from our particular vantage point means either that we are in a cosmologically special location, that there is a common physical cause for all the anomalies, or that they are all systematic artifacts that happen to correlate. The first option, that we are special, violates the Copernican principle, the centuries-old assumption that there is nothing privileged about our position in the universe. But the Copernican principle is itself a consequence of the cosmological principle. If the cosmological principle is wrong, the Copernican principle may be wrong too. The second option, a common physical cause, is exactly what the topological defect monopole model provides. If we sit off-center inside a horizon-scale domain wall structure, the gradients in the scalar field naturally produce correlated dipoles in all field-dependent quantities: alpha, the cosmological constant, and matter density. The alignment is automatic. The third option, correlated systematics, becomes progressively harder to sustain as more independent measurements pile up. I spent an unreasonable amount of time reading the primary literature on this, and I want to tell you honestly where I landed. I do not know if the alpha dipole is real. Nobody does. The systematic error question is genuine and unresolved. The wavelength calibration distortions in Keck and VLT are large enough to fake the signal. The ESPRESSO null result on a single line of sight is consistent with either the dipole or no variation. The magnesium isotope ambiguity means that even the most precise measurements may be contaminated by an assumption we cannot verify. But the pattern of anomalies pointing in the same direction on the sky, that is harder to dismiss. And the fact that it has not received the attention it deserves, that it sits in the technical literature where only specialists encounter it, while popular science continues to present the cosmological principle as settled fact. That bothers me in a way I did not expect when I started researching this. This is published, peer-reviewed physics. Multiple groups, multiple techniques, multiple sigma. And the implication if confirmed, is that the laws of physics are not the same everywhere, that the universe has a preferred direction, and that everything we have calculated about dark energy and the expansion history and the ultimate fate of the cosmos may be based on an assumption. That is wrong. That should have made headlines. It did not. Let me take you back to the number itself, because I think the full weight of what a varying alpha means does not land unless you understand what alpha actually does, not at the level of it controls electromagnetism, at the level of specifics, at the level of your body and the stars that made it. Arnold Sommerfeld introduced the fine structure constant in 1916. He was trying to explain why the spectral lines of hydrogen, which Niels Bohr's model predicted should be single sharp lines, were actually split into closely spaced multiplets. Bohr's model treated the electron as moving in a circular orbit. Sommerfeld showed that if you allowed elliptical orbits and included the effects of special relativity, the energy levels depended not just on the principal quantum number, but also on the orbital angular momentum. The splitting between these energy levels was proportional to alpha squared. Hence the name, fine structure, the fine detail in spectral lines, and alpha, the constant that governed how large the splitting was. Alpha is defined as E squared divided by 4 pi times epsilon 0 times h bar times c. The electron charge squared divided by the permittivity of free space divided by the reduced Planck constant divided by the speed of light. It is a ratio of fundamental constants that collapses into a single, dimensionless number, and it appears everywhere in physics. It determines the size of atoms. The Bohr radius, the characteristic size of a hydrogen atom, is inversely proportional to alpha. If alpha were larger, atoms would be smaller. If alpha were smaller, atoms would be larger. The ionization energy of hydrogen, the energy needed to rip the electron away from the proton, scales as alpha squared. The strength of chemical bonds depends on alpha. The rates of chemical reactions depend on alpha, because reaction rates depend on the energy barriers between molecular configurations, and those barriers are set by electron energies, which depend on alpha. But atoms and chemistry are just the beginning. Alpha determines whether stars can make carbon. And this is where the story reaches a depth that Pauli, dying in room 137, never got to see. In 1953, Fred Hoyle was trying to solve a problem. The universe appeared to contain a large amount of carbon. Carbon is the fourth most abundant element in the universe by mass and the foundation of all known biochemistry. But the astrophysics of how carbon is made in stars seemed to forbid it. The triple alpha process, the nuclear reaction that fuses 3 helium-4 nuclei into 1 carbon-12 nucleus, has a problem. 2 helium nuclei first fuse to form beryllium-8. But beryllium-8 is spectacularly unstable. It decays back into 2 helium nuclei in about 10 to the minus 16 seconds. In that impossibly brief window, a third helium nucleus has to slam into the beryllium-8 and stick, forming carbon-12. The probability of this happening is vanishingly small unless there is a resonance, an excited state of the carbon-12 nucleus that has almost exactly the right energy to match the combined energy of the beryllium-8 plus the incoming helium-4. Hoyle predicted that this resonance must exist, based on the simple observation that carbon exists and that therefore the nuclear physics must permit it. He traveled to Caltech and convinced Willie Fowler's nuclear physics group to look for it. They found it. The Hoyle state at 7.654 MeV sits about 380 keV above the beryllium-8 plus alpha threshold. That energy gap is crucial. If the Hoyle state were a few hundred key lower, it would not be a resonance, and the triple alpha process would be too slow to produce significant carbon. If it were higher, even more carbon would be produced, but it would all be processed further into oxygen, leaving no carbon behind. Here is where alpha enters. The energy of the Hoyle state depends on the strong nuclear force, which is governed by the strong coupling constant alpha sub s. But it also depends on the electromagnetic force, because the protons in the carbon nucleus repel each other via the Coulomb interaction, and the strength of that repulsion is governed by alpha. The exact position of the Hoyle state relative to the threshold is determined by a delicate balance between these two forces. Change alpha by a few percent and the balance shifts. The resonance moves. Carbon production either collapses or runs away, converting everything to oxygen. How sensitive is it exactly? In 2013, Evgeny Eppelbaum, Hermann Krebs, Timo Lade, Dean Lee, and Ulf Günther Meissner published a landmark paper in Physical Review Letters, Volume 110, Article 112502. They used lattice effective field theory calculations to compute the dependence of the Hoyle state energy on the fundamental parameters. What they found was that the triple alpha process can tolerate changes in the fundamental constants of about 2 to 3% before carbon and oxygen production is significantly disrupted. That is not a razor's edge. It is a window, but it is not a wide open window either. The popular claim that if alpha were different by even 1%, life would be impossible is an exaggeration. The actual constraints are more forgiving than that. Adams's 2019 review confirmed this, finding a substantial region of parameter space where complex chemistry and stellar nucleosynthesis could function. The universe is not as finely tuned as the most dramatic accounts suggest. But here is the thing. 2 to 3% is the tolerance for carbon production. The alpha dipole, if real, implies a variation of about 10 parts per million across the observable universe. That is a factor of 1,000 below the threshold, where chemistry starts to change. At the current observed level, the dipole does not threaten life anywhere in the observable universe. The periodic table works everywhere we can see. The question is what happens beyond the observable horizon. And here the implications become genuinely unsettling, because we have no data and the theoretical landscape offers no constraints. If alpha varies by 10 parts per million across 10 billion light years, what does it vary by across 100 billion light years? A trillion? The observable universe is a sphere roughly 93 billion light years in diameter, but the actual universe, the part that is physically real but beyond our ability to observe because light from there has not had time to reach us, could be vastly larger. Some estimates from inflationary cosmology suggest the full universe could be 10 to the 23 times larger than the observable part. Others suggest it could be infinite. If alpha has a gradient, if it varies in space, then at some distance from us, in some direction, alpha takes values where carbon cannot form, where atoms have different sizes, where the periodic table has different elements or no elements at all, where the laws of chemistry are not the laws of chemistry you learned in school, but something unrecognizable. We cannot see those regions. We will never be able to see them. The light from there will never reach us because the expansion of the universe is pulling them away faster than light can travel. But if the dipole is real, those regions exist, and the boundary between the universe that makes us and the universe that cannot make us is not a wall or a barrier. It is a gradient, a smooth transition, a place where the numbers change slowly, continuously, over distances too vast to traverse, from values that permit life to values that do not. And we are not at the center of the habitable zone. The dipole implies we are somewhere on the gradient. Alpha is slightly different, 10 billion light years in one direction, than it is 10 billion light years in the opposite direction. We are not at the extremes, or we would not be here. But we are not at the center either, or the dipole would be zero. We are at some specific, non-special position on a cosmic gradient of habitability. Think about what that means for the question of why the fine structure constant has the value it does. It does not have the value it does. It has the value it does here, at this position in the gradient, at this particular spot in a universe that is not uniform, that does not have the same rules everywhere, that is not the symmetric, isotropic, everywhere the same cosmos that cosmology promised you. The number that Pauli died thinking about, the number that Feynman called the greatest mystery in physics, may not be a universal constant at all. It may be a local coordinate, an address, a description of where you are standing in a landscape of possibilities. Eddington tried to derive alpha from pure logic. He believed the number 136, which he later revised to 137, could be calculated from the number of independent components of the Dirac equation in a curved space-time. He published this in his 1936 book Relativity Theory of Protons and Electrons. And it was, to be direct about it, wrong. The experimental value was already known to be closer to 137.036, and Eddington's derivation produced an exact integer. His colleagues were embarrassed for him. The whole episode is treated in the physics community as a cautionary tale about the dangers of numerology. But there is a way to read Eddington's failure that is more interesting than the standard moral. Eddington's mistake was not that he tried to derive alpha from deeper principles. His mistake was that he assumed alpha had a single, universal, derivable value. If alpha varies, if it is different in different places, then it cannot be derived from first principles because it does not have first principles value. It is a field. It is a function of position. Eddington was trying to derive a house number as if it were a law of mathematics. The number is real, but it describes a location, not a principle. Pauli's obsession looks different in this light too. He spent decades agonizing over why alpha was 1/137. He died in room 137. He never found the answer. And the reason he never found the answer may be that the question was wrong. He was asking, why this number, when the real question was, why this number here? That reframing from universal constant to local parameter is what makes the alpha dipole so much more consequential than a measurement controversy about spectrograph calibration. If the number that governs all of electromagnetic physics is a local parameter, then the laws of physics as we know them are local. Parochial, a description of how things work in our neighborhood, not a description of how things work. And the neighborhood, according to the best data we have, is not centered on us. It has a gradient, it has a direction, and that direction lines up with the same direction that the cosmic microwave background anomalies point, and the same direction that the dark energy asymmetry points, and the same direction that the quasar count dipole points. Coincidence or cause? Those are the options. And right now, nobody can tell you which one it is. I want to come back to the people now, because the human story inside this measurement controversy reveals something about the sociology of physics that I think is worth saying out loud. John Webb has been working on this problem for over 25 years. He first published evidence for a varying alpha from Keck data in 1999 in Physical Review Letters. He was a professor at one of Australia's top universities. He had strong institutional backing. He had Victor Flambaum, one of the world's leading atomic theorists, as his close collaborator. He published in the best journals. He won national prizes. And still, a quarter century later, the result occupies a kind of scientific limbo. It has been neither refuted nor confirmed, and it has not engaged enough people to generate the follow-up measurements that would settle it. Think about what that does to a career. 25 years of publishing results that the community acknowledges are interesting, that they agree are technically sound, that they concede are consistent with the data, but that they refuse to invest the telescope time and institutional effort needed to definitively test. Webb has not been suppressed in the dramatic sense. Nobody has denied him publication. Nobody has questioned his competence. The mechanism is more subtle and arguably more effective. It is the soft power of disinterest, the casual agreement that this is probably systematics, followed by a change of subject. The implicit message that pursuing this question too aggressively marks you as someone who does not understand the practical culture of modern observational cosmology. I am speculating about the personal toll. I do not have quotes from Webb about what this has been like. What I have is his public statement from 2024, carefully worded and scrupulously honest, that we do not have definitive evidence of space-time variations. That is the statement of a man who has spent 25 years on a result and will not oversell it. Whether that restraint is admirable caution or evidence of how thoroughly the institutional pressure to conform shapes even the people making the uncomfortable discoveries, I genuinely do not know. Michael Murphy's trajectory is also instructive. Murphy was part of Webb's original team. He co-authored the early Keck papers. He won the Eureka Prize alongside Webb. And then he published the supercalibration paper in 2015, showing the wavelength distortions. He was not working against Webb. He was doing what good science requires, testing the result with independent methods. But the effect was that the most prominent critique of the alpha dipole came from within Webb's own former collaboration. The physics community took this as confirmation of the probably systematics interpretation. What it actually showed was that the systematic errors exist and are large, but whether they account for the signal is a separate question that the supercalibration paper did not definitively answer. Dumont and Webb's response showed the signal survives correction, at least approximately. That nuance was largely lost. This is the pattern I keep encountering. The more I read about the history of uncomfortable results in physics, the initial publication generates excitement. A challenge appears that offers a mundane explanation. The community adopts the mundane explanation, not because it has been proven correct, but because it is sufficient to restore the default assumption, sufficient to avoid the disruptive implication, sufficient to justify redirecting attention elsewhere, and the original result enters a limbo where it is neither confirmed nor refuted, just indefinitely deferred. David Bohm's hidden variable interpretation suffered the same fate in 1952. John Bell's theorem languished for years because the questions it raised were considered unprofessional. Hugh Everett's many-worlds interpretation was dismissed by Niels Bohr in a single conversation, and its author left physics entirely, dying of a heart attack in 1982 at the age of 51. His daughter killed herself in 1996, leaving a note that said she was going to join her father in a parallel universe. Everett's theory, dismissed for decades, is now taken seriously by a significant fraction of theoretical physicists. Too late for him. I am not saying the alpha dipole will follow this pattern. Maybe it is systematics. Maybe Andes on the ELT will publish a definitive null result in 2032, and the whole episode will become a textbook example of how instrumental artifacts can mimic cosmic signals. That is entirely possible. But the way the result has been handled, the soft institutional indifference, the failure to prioritize definitive follow-up, the casual certainty that it is probably wrong before the definitive test has been done, that pattern has a history, and the history does not reflect well on the institutions. Let me address a misconception now, because I think it is important for understanding what is actually being claimed and what is not. The popular framing of this story, when it appears at all, tends to be something like, scientists discover the laws of physics are different in another part of the universe. That is not what the data shows. What the data shows is that the fine structure constant may have a spatial gradient of about 10 parts per million across the observable universe, with a dipolar pattern. Alpha is not wildly different somewhere else. It is fractionally different by an amount that has zero practical effect on chemistry, biology, or the periodic table within the observable universe. Nobody is saying that somewhere out there atoms are falling apart or the electromagnetic force has turned off. The variation, if real, is tiny. But the significance of the result is not in the size of the variation, it is in the principle. The cosmological principle says the laws of physics are exactly the same everywhere, not approximately the same, not the same to within 10 parts per million, exactly the same. A variation of any size, confirmed at any significance, would violate it, and a violation of the cosmological principle, regardless of how small, invalidates the mathematical framework on which modern cosmology is built. This is analogous to the discovery that the universe's expansion is accelerating. The acceleration is tiny. The cosmological constant, expressed in natural Planck units, is about 10 to the minus 122. It is the smallest non-zero parameter in all of physics. It has almost no effect on local physics, on galaxies, on stars, on daily life. But its existence overturned the assumption that the expansion was decelerating and led to the introduction of dark energy, which now dominates the energy budget of the universe and drives its ultimate fate. The size of the effect was irrelevant. What mattered was that it was non-zero. The alpha dipole, if confirmed, is the same kind of result. The size does not matter. What matters is that it is there. There is another misconception I want to correct. Several popular accounts describe the alpha dipole as pointing at Earth and treat this as suspicious, as if the data is claiming we are at the center of some cosmic anomaly. This is a misunderstanding of what a dipole is. A dipole is a vector field. It has a direction. The axis of the dipole, by geometrical necessity, passes through the observer, whoever and wherever the observer is. If you were standing on a planet in the Andromeda galaxy and you measured the same alpha dipole, the axis would pass through you. The dipole points at us is true, but meaningless in isolation. What is not meaningless is the direction the dipole points, because that direction can be compared to other independently measured preferred directions. And that comparison, the alignment of the alpha dipole with the dark energy dipole, the CMB anomalies, and the quasar count dipole, is the result that elevates this from an interesting measurement controversy to something genuinely consequential for cosmology. The individual anomalies are each debatable, the alignment between them at the level of 10 to 20 degrees, with a joint probability under isotropy of less than 1 in a million, is what changes the character of the evidence from maybe to something is going on and we need to figure out what. Let me add one more piece to this puzzle, because it landed in the literature recently and almost nobody outside the specialist community seems to have noticed. In addition to all the anomalies I have described, there is now evidence from gamma ray propagation that the universe may not be transparent in the same way in all directions. Studies of the spectra of blazars, the active galactic nuclei that beam relativistic jets directly towards us, have found hints that the opacity of the universe to very high-energy gamma rays varies with direction on the sky. This is tentative, and I want to flag it as less mature than the alpha and CMB anomalies, but it is another data point suggesting directional asymmetry, another vector pointing into the same region of the sky. And there are the radio source counts. Independent of the Catwise infrared quasar catalog, radio surveys have been used to test the cosmological principle by counting radio galaxies in different directions. The results are mixed. Some analyses, like John Darling's 2022 study, using the Very Large Array Sky Survey and the Rapid ASCAP Continuum Survey, found the radio dipole consistent with a kinematic expectation, and therefore consistent with the cosmological principle. Others found excess amplitude in roughly the same direction as the Catwise anomaly. The field is actively contested. I want to be honest about the uncertainty here, because I think the audience for this kind of content is smart enough to handle nuance. Not all the data points in the same direction. Not all the analyses agree. The picture is messy, which is exactly what you would expect at the frontier of observational cosmology, where the signals are small and the systematics are comparable in size. But the messy picture is more consistent with something real is being detected at the edge of our instrumental capabilities, and the systematic errors have not yet been fully sorted out, than it is with there is nothing there, and all these independent groups using independent methods are seeing correlated artifacts by coincidence. Quote, "Science rarely resolves neatly at the moment of first detection. The acceleration of the expansion took years to move from contested to consensus. Gravitational waves were first detected by LIGO in 2015 and announced in 2016, but the indirect evidence from the Hulse-Taylor binary pulsar had been accumulating since the 1970s. Scientific revolutions are almost never clean. They are almost always preceded by a period exactly like this one, where the data is suggestive but not definitive, where the anomalies are real but the explanations are disputed, where the institutional response is caution bordering on avoidance. The question is whether we are in that period right now, and the answer will come from a 39-meter mirror in the Atacama Desert, sometime around 2032. Until then, the question is open, genuinely, uncomfortably, consequentially open. There is another way to constrain alpha variation that comes not from telescopes but from a 2-billion-year-old natural nuclear reactor in Gabon. In 1972, French scientists analyzing uranium ore from the Oklo mine in the Republic of Gabon discovered something that should have been impossible. The isotope ratios of the uranium were wrong. Specifically, the ratio of uranium-235 to uranium-238 was significantly depleted compared to what you find everywhere else on Earth and in every meteorite sample. The explanation was stunning. Roughly 1.7 billion years ago, when the uranium-235 concentration was high enough to sustain a chain reaction, a natural fission reactor had operated in the Oklo ore deposit. The reactor had run on and off for several 100,000 years, moderated by groundwater, producing energy and transmuting elements in the rock. The reason Oklo matters for this story is that nuclear fission reactions are sensitive to the fine structure constant, the cross-sections for neutron capture, the energy levels of the nuclear resonances that determine which reactions proceed and which do not, all depend on alpha. In 2004, Steve Lamoureux and Justin Torgerson at Los Alamos National Laboratory published an analysis of the samarium isotope ratios in the Oklo reactor products and concluded that alpha could not have changed by more than about 4.5 parts in 10 to the 8 over the 1.7 billion year lifetime of the reactor. That is a constraint at the level of about 0.5 parts per million per billion years, roughly consistent with the Webb result. But the Oklo constraint is a temporal constraint at one spatial location. The same limitation that plagues the atomic clock tests and the ESPRESSO single line of sight measurements. It tells you that alpha did not change much at this spot on Earth over 1.7 billion years. It does not tell you whether alpha is the same in the direction of Ara as it is in the direction of Butez. The spatial question remains unanswered. And this is the fundamental asymmetry that makes the alpha dipole so difficult to test and so easy to defer. Every high-precision constraint we have is either temporal at one location or spatial along one line of sight. The dipole is a spatial pattern across the full sky. Testing it requires measuring alpha at many positions scattered across the sky with uniformly high precision. That requires enormous amounts of telescope time on the world's best instruments. Telescope time is allocated by committees. Committees have priorities, and rechecking a contested 2011 result about spectrograph calibration does not compete well against discovering new exoplanets or measuring the Hubble constant to higher precision, or any of the other established research programs that have institutional momentum behind them. This is the mechanism of deferral. It is not suppression. It is prioritization. And the priorities are set by a community that has already decided, informally and without explicit deliberation, that the alpha dipole is probably an artifact. The circular logic is invisible to the people inside it. We do not prioritize testing the result because we think it is probably wrong. We think it is probably wrong because nobody has tested it. The definitive test never happens because the will to conduct it never forms. I want to put one more thing in front of you before I reach the end of this, because I think it grounds the abstraction in something tangible. Right now, in your body, there are roughly 37 trillion cells. Each of those cells contains DNA, a double helix held together by hydrogen bonds. The strength of a hydrogen bond is governed by the electromagnetic interaction, which is governed by alpha. The base pairs in your DNA, adenine bonding to thymine, guanine bonding to cytosine, are held at specific distances and specific angles by electrostatic forces whose magnitudes depend on the fine structure constant. The enzymes that read your DNA, the polymerases that copy it, the ribosomes that translate it into proteins. All of these molecular machines operate within energy tolerances that are set, ultimately, by the value of alpha. If alpha were a few % different, those tolerances would shift. The hydrogen bonds would be slightly stronger or slightly weaker. The base pair geometries would change. The error rates in DNA replication would change. The folding patterns of proteins would change. Life as we know it might still be possible with a slightly different alpha, perhaps even more robust in some ways, but it would not be this life. Your DNA would encode different proteins. Your biochemistry would run at different rates. You would be, at the molecular level, a different kind of organism. At 5 to 10 parts per million, none of this matters. The variation is too small to affect any biochemical process. Your body would function identically at alpha equals 1 over 137.0359 and at alpha equals 1 over 137.03. 4, 6, 1. The difference is in the 14th decimal place of the bond energies. It is unmeasurable in any biological context, but the principle remains. If alpha can vary, then the chemistry that makes you possible is not guaranteed everywhere. It is a local fact. true in this patch of the universe, not necessarily true in that one. And the boundary between where your chemistry works and where it does not is somewhere out there, beyond the horizon, invisible and unreachable, defined by a gradient in a scalar field that was set during the first moments of the universe and has been frozen in place ever since. You are, in this picture, a phenomenon that depends on local conditions, not just on your planet or your solar system or your galaxy, on your location in the field, on the value the scalar takes at the coordinates where you happen to exist. Change the coordinates by enough, and you do not exist. Not because of anything violent, not because of an explosion or a catastrophe, because the hydrogen bonds are too weak, because the nuclear resonances do not line up, because carbon is not produced in stars at that position, because the rules, the quiet background rules that make your atoms hold together and your cells divide and your neurons fire, are slightly different there. Just slightly, but enough. That is what a varying fine structure constant means at the level of lived experience. It means that your existence is not a consequence of universal law. It is a consequence of position, of address, of where in the landscape of possible physics you happen to be standing. And the dipole, if it is real, is the first evidence that the landscape is not flat. I want to take you somewhere now that goes beyond the measurements, beyond the spectrographs and the calibration disputes and the sigma values, because there is a philosophical implication hiding inside the alpha dipole that I think is the real reason this result makes physicists uncomfortable, and it has nothing to do with systematic errors. For as long as modern physics has existed, the constants of nature have been treated as fundamental. Not just measured values, fundamental, the speed of light, Planck's constant, the gravitational constant, the fine structure constant. These were supposed to be the bedrock numbers, the given parameters of the universe, the values that any complete theory of everything would either derive or accept as axiomatic. They were supposed to be the same in every laboratory, in every galaxy, in every era, from the first microsecond after the Big Bang to the heat death 100 trillion years from now. This was not just an empirical observation. It was a metaphysical commitment. The laws of physics are the laws of physics. They do not change. They do not depend on where you are. They are not contingent. Paul Dirac challenged this in 1937 with his large numbers hypothesis. He noticed that certain dimensionless ratios in physics, like the ratio of the electromagnetic force to the gravitational force between a proton and an electron, which is about 10 to the 36, were of a similar order to the ratio of the age of the universe to the characteristic timescale of atomic processes. Dirac proposed that these large number coincidences were not coincidences at all, but reflected deep relationships between the constants, relationships that would require some of the constants to change with time as the universe ages. If the ratio had to stay fixed and the age of the universe is increasing, then one of the other quantities must be changing too. Dirac's hypothesis was largely dismissed because precise measurements of the gravitational constant showed no variation at the level his hypothesis predicted. But the idea that the constants might not be constant never fully died. It resurfaced in the 1980s with the development of string theory and the realization that what we call fundamental constants might actually be properties of the vacuum state, the ground state of the quantum fields that fill all of space. In string theory, the values of the coupling constants, including alpha, depend on the shapes and sizes of the extra dimensions that are compactified below the scale we can observe. If those extra dimensions have different configurations in different regions of the universe, or if they evolve differently in the early universe, then the coupling constants would differ accordingly. This was the seed of the landscape idea. In 2003, Leonard Susskind at Stanford published a paper that formalized the concept of the string theory landscape. There were roughly 10 to the 500 different stable or metastable vacuum configurations predicted by the string theory equations, each with different values of the fundamental constants. The actual number might be even larger. Each vacuum state is like a valley in an enormously high-dimensional energy landscape. Our universe sits in one particular valley, with one particular set of constants. Other valleys have different constants, and eternal inflation, the process by which the universe undergoes exponential expansion driven by quantum fluctuations, constantly creates new regions of space that can settle into different valleys. The landscape is not a hypothesis about the alpha dipole. It was developed independently, motivated by entirely different problems, primarily the cosmological constant problem, the notorious fact that quantum field theory predicts a vacuum energy about 120 orders of magnitude larger than what is observed. And the only known resolution within string theory is that we happen to live in a valley where the vacuum energy is anomalously small. But the landscape provides the natural theoretical context for a varying fine structure constant. If the fundamental constants are properties of the vacuum state, and the vacuum state can differ between regions of space, then the constants can vary in space. That is not an exotic addition to the theory. It is a built-in feature. What the alpha dipole would represent, in this framework, is the first observational evidence that we are not in a uniform vacuum, that the vacuum state of our region of the universe is not the same as the vacuum state of regions in the opposite direction, that the boundary between vacua, the domain wall, is not infinitely far away, but within or near our observable volume. This is where the vertigo sets in, because if the vacuum state is not uniform, then what we call the laws of physics are not laws in the traditional sense. They are not universal truths discovered by human intellect. They are local conditions, properties of the particular valley our universe occupies. True here, not necessarily true there. Contingent on accident, on where the field settled during the first fractions of a second after whatever event created our local patch of space-time. The constants of nature, in this view, are not fundamental. They are environmental. They are more like the temperature of the room than like the axioms of mathematics. They describe the state of the system, not the rules that govern the system. And the rules, whatever they are, the deeper layer that determines which vacuum states are possible and how likely each one is, those rules might not even specify the constants. They might leave them free, undetermined, subject to variation in space and time. I still do not know how to think about this. I have been reading the literature for weeks, and I find myself oscillating between thinking it is the most important possibility in modern physics and thinking it is an artifact of our inability to resolve spectrograph calibration errors. Both are possible. The evidence does not pick a winner, and the experience of genuinely not knowing, of sitting with the uncertainty, of being unable to close the loop, is exactly the experience that the physics itself is pointing toward. Because here is what struck me most deeply as I went through the papers. Every experiment, every analysis, every follow-up study runs into the same wall. The systematic errors are comparable to the signal. The calibration uncertainties are of the same order as the claimed variation. The magnesium isotope ratios are unknown and unknowable at the distances being measured. Every attempt to settle the question runs into a limit that is not technological, but in some sense fundamental. A limit on what can be known from the vantage point of a single planet orbiting a single star in a single galaxy, in what might be a small and parochial patch of a much larger and much stranger cosmos. There is a philosophical position called structural realism that holds that we can know the structure of reality, but not its underlying nature. The equations are real. The relationships between quantities are real. But the entities that populate those equations, what they ultimately are, may be beyond the reach of human inquiry. The alpha dipole, if it is real, suggests a variant of this problem. We can know the local values of the constants with extraordinary precision. We can verify that electromagnetism works the way we think it works, in our laboratories, in our solar system, in our galaxy. But whether those values are universal, whether they extend beyond the horizon, whether they describe the universe or just our neighborhood of it, that may be a question we cannot answer from here. And that is deeply, unavoidably uncomfortable, because modern physics is built on the assumption that the laws discovered in terrestrial laboratories apply everywhere. This is not a minor assumption. It is the assumption that makes astrophysics possible. When we say a star 10 billion light-years away is made of hydrogen, we are assuming that the spectral lines of hydrogen are the same there as here. When we measure the expansion rate of the universe using type Ia supernova, we are assuming the nuclear physics that produces the explosion and the electromagnetic physics that produces the light are the same everywhere. When we calculate the age of the universe from the CMB, we are assuming the physics of recombination. The moment when the universe cooled enough for atoms to form was the same as it would be in our laboratories. If alpha is different in different directions, every one of those assumptions acquires an asterisk. Every measurement of cosmic distance acquires an uncertainty that we do not know how to estimate, because we do not know the functional form of the alpha variation beyond the observable universe. Every statement about the properties of distant objects becomes conditional on an assumption that the data itself suggests might be wrong. The foundations do not crumble, they soften, they become contingent. And physics, which has spent 400 years building ever more precise measurements on the assumption that the ground underneath is solid, discovers that the ground might be shifting, slowly, by 10 parts per million over 10 billion light-years. But shifting. I mentioned earlier that Feynman called alpha a magic number written by the hand of God. There is a darker reading of that phrase now. If alpha varies, then God's hand was not writing a single number. It was painting a gradient, and we have been reading one point on the gradient, one tiny patch, and mistaking it for the whole painting. Let me tell you about one more connection that almost nobody has drawn, because I found it in the literature and I think it deserves attention. In 2012, Mariano and Perry Voloropoulos noted in their analysis that the direction of the alpha dipole lies within or very near the preferred plane defined by the CMB quadrupole and octupole. This plane is sometimes called the ecliptic alignment because it is roughly aligned with the plane of the solar system's orbit around the Sun. This coincidence was one of the most troubling aspects of the original axis of evil discovery. A cosmic anomaly should not align with a local, solar system-defined frame. The standard explanation has been that it is a residual foreground artifact, something related to the zodiacal dust cloud or the motion of the solar system through the local interstellar medium. Planck investigated this thoroughly and concluded that the alignment persists after foreground removal, but that its significance may be inflated by the particular choice of statistical test. But here is the uncomfortable part. If the alpha dipole, measured from quasar absorption spectra that have absolutely nothing to do with the solar system or the ecliptic, also lies near the ecliptic plane, then the foreground explanation for the CMB alignment becomes harder to sustain. You cannot invoke zodiacal dust to explain why quasar absorption lines 10 billion light-years away show a preferred direction near the ecliptic. The quasars do not know where the ecliptic is. This is where the coincidence or cause question becomes most acute. Either we are seeing a genuine large-scale anisotropy in the universe that happens by coincidence to align roughly with the ecliptic plane as seen from Earth, or there is some unknown systematic effect that contaminates both CMB analysis and quasar spectroscopy in a way that produces ecliptic-aligned anomalies. Or we are misunderstanding something fundamental about our place in the cosmos. None of these options is comfortable. And that is, I think, the real reason this body of evidence has not been synthesized for public consumption. It is not that the individual results are too technical. They are not. Any intelligent person can understand what a dipole is and what it means for multiple dipoles to align. The reason it has not been communicated is that the implication sits in a space that institutional science does not like to occupy. The space between we have detected something and we know what it means. The space where the data is real, but the interpretation is unresolved. The space where every honest physicist would have to say, I do not know, and mean it. That space is exactly where we are right now. Let me bring this back to where it started, to the number, to room 137, to the question that consumed Pauli and that physics has still not answered. When Pauli was working on the fine structure constant in the 1930s and 40s, the measured value was consistent with exactly 1/137. As measurements improved, the value moved. It became 1/137.03599. And then more decimal places followed, and the hope that the number was a simple ratio or derivable from integers died. But the obsession did not. Because even with 11 decimal places of precision, even after the 2022 CODATA evaluation nailed it to 1/137.035,999,177, with a relative uncertainty of 1.5 parts per 10 billion, nobody can explain why. This is not a failure of effort. Generations of physicists have attacked this number. Sommerfeld introduced it, Eddington tried to derive it and failed. Pauli spent decades on it and died in its shadow. Feynman described it as the greatest mystery in physics and admitted no human had ever understood it. The standard model of particle physics, which is the most precisely tested theory in the history of science, takes alpha as an input parameter. It does not predict it, it does not explain it, it just uses it. Quantum electrodynamics, the quantum field theory of the electromagnetic interaction, predicts the anomalous magnetic moment of the electron to 12 significant figures, and the prediction matches the measurement to 12 significant figures. It is the most precise agreement between theory and experiment ever achieved in any field of science, and the entire calculation depends on alpha being a known input. If you ask where alpha comes from, QED has no answer. It was measured. That is all. The standard model as a whole has 19 free parameters, 26 if you include neutrino masses and mixing angles. These are numbers that the theory cannot predict. They are measured experimentally and plugged in by hand. Alpha is one of them. The Higgs boson mass is another. The quark masses, the lepton masses, the mixing angles, the QCD coupling constant, all of these are free parameters that the theory treats as given. For decades, the expectation was that a more complete theory, a theory of everything, a grand unified theory, a theory of quantum gravity, whatever it turned out to be, would reduce the number of free parameters, would derive some of the constants from first principles, would explain why alpha is 1/137, and not some other number. The string theory landscape destroyed that expectation. If there are 10 to the 500 possible vacuum states, and the constants take different values in each one, then there is no derivation. The constants are not fundamental. They are environmental. And the question why 137 becomes why 137 here, which the anthropic principle answers with a shrug. Because we can only be here if alpha is close to this value. If it were very different, we would not exist to ask the question. That is not a satisfying answer, but it may be the only one available. And the alpha dipole, if it survives the next decade of scrutiny and the next generation of instruments, would be the empirical vindication of that dismal conclusion. It would confirm that alpha is not a universal constant, but a local variable, that the fine structure constant in the direction of Ara is not quite the same as the fine structure constant in the direction of Coma Berenices, that the number Pauli died thinking about is not etched into the fabric of reality, but painted onto it in a pattern that shifts so slowly across the sky that you need billion-year-old photons and the most precise spectrographs ever built to detect the gradient. And still we would not know where the gradient leads. We would not know what alpha becomes beyond the horizon. In the regions of the universe we can never observe. We would not know whether there is a region where it crosses the threshold at which the Hoyle resonance fails and carbon cannot form, where the periodic table is not our periodic table, where the chemistry that builds you and me and every living thing does not function. We would know that such regions are theoretically possible. We would know that the gradient points in their direction, but we could never reach them, never observe them, never verify that they exist. The universe in this picture is not a uniform stage on which a single set of physical laws plays out. It is a patchwork, a landscape of local conditions, each patch obeying local rules. The patch is stitched together by gradients in scalar fields that no one on any one patch can see the full extent of. And we are embedded in one patch, measuring the rules of that patch with exquisite precision, and only just now beginning to suspect that the rules we measured are not universal truths, but regional bylaws. This is the implication that I think sits at the bottom of this story, underneath the spectrograph calibration debates and the sigma values and the institutional politics. It is the possibility that physics has been asking the wrong type of question for a century. Why does this constant have this value? Assumes the constant has a value, singular, universal, the same everywhere and always. If the alpha dipole is real, the question is not why. The question is where. Where in the landscape of possible physics are we? Where on the gradient? How close to the edge? And there is one more thing that I cannot stop thinking about. The alignment. The fact that the direction where alpha appears to differ most from us, the direction of the dark energy dipole, the direction of the quasar count XS, is not random. It is correlated. Multiple independent probes of the large-scale universe, using different physics, different instruments, different teams, different methods, all pointing within about 10 degrees of the same spot on the sky. If you asked me to design a universe that was trying to tell an observer something, trying to leave a signal that something about their location in the cosmos was not what they assumed, I do not know how you would make that signal clearer than this. Multiple independent channels, multiple independent teams discovering the signal independently. A joint probability of alignment under the null hypothesis of less than 1 in a million. And a single instrument, not yet built, that will tell us whether all of it is real or all of it is noise. The ELT ANDS 2031, maybe 2032, the most precise spectrograph ever constructed, mounted on the largest optical telescope ever built, pointed at quasars scattered across the sky, measuring the fine structure constant at 10, 15, 20 positions with 0.3 parts per million precision. If Anders sees the dipole, the cosmological principle falls, not loudly, not with a single dramatic paper. It will fall the way it has been eroding, slowly through accumulating evidence that the universe is not as symmetric as we assumed, that there is a direction, that there is a gradient, that the ground we built modern cosmology on was not quite level. If Anders sees nothing, the dipole dies. Webb's quarter-century of work becomes a cautionary tale about systematic errors in a shell spectroscopy. The cat-wise anomaly and the CMB alignment would need separate explanations, and each would probably get one, a foreground here, a calibration error there, a statistical fluke in this catalogue. The anomalies would dissolve individually, even if their collective alignment remained uncomfortable. I do not know which outcome I expect. I genuinely do not. I have read the papers. I have followed the arguments. I have tracked the calibration debate through Whitmore and Murphy and Dumont and Webb and Kotis and Milakovic and the ESPRESSO team. And the data does not tell me which way this will go. What it tells me is that the question is real, that it matters, that the answer will either confirm the most basic assumption in cosmology or overturn it, and that, for reasons I find difficult to fully articulate but impossible to ignore, almost nobody is treating it with the urgency it deserves. In Zurich, in 1958, Wolfgang Pauli lay in a hospital bed in room 137 and knew he was going to die. The number that had haunted him for decades was printed on the door. He had spent a career trying to understand why the fine structure constant had the value it did. He had consulted with Carl Jung about whether the number had mystical significance. He had written letters about it to colleagues that bordered on desperation, and he died without an answer. 66 years later, the question he was asking may have been the wrong question. Not, why this number, but why this number here? And the only instrument that can answer it is being assembled, segment by segment, mirror by mirror, in a desert in Chile, on top of a mountain that was chosen for the clarity of its sky. The sky over the Atacama is among the darkest on Earth. On a clear night, you can see the Milky Way so brightly it casts shadows. And somewhere in that sky, in the direction of the constellations Ara and Triangulum Australe, there is a line of sight along which the fine structure constant may be different from the one measured in every laboratory on this planet. A line along which the number that Pauli spent his life trying to understand begins to shift by a few parts per million, then more, until, at some distance we cannot see and will never visit, the number that governs whether atoms hold together, whether stars forge carbon, whether DNA folds into the double helix that carries your genetic code, ceases to be the number it is here and becomes something else, something that does not build what we are built from, something that does not permit what we are. The data has been sitting in the literature since 2011. The alignment with the dark energy dipole was published in 2012. The cat-wise confirmation came in 2021. The ESPRESSO precision measurements are ongoing. The thorium nuclear clock enhancement factor was measured in 2025, and the question remains open, whether the laws of physics are the same everywhere, or whether we are sitting in a patch of the universe where the numbers happen to work, surrounded by a vastness where they do not, separated from it by a gradient so slight that it took billion-year-old light and the most sensitive instruments humanity has ever built to detect even the faintest suggestion that it might be there. Pauli died in room 137. He thought the number was trying to tell him something. He may have been right, but the message was not what he expected. The message was not, "Here is why I have this value." The message was, "I do not have one value." And we are only now, 66 years later, beginning to hear it.